Good afternoon, everyone. How's everybody doing? Good? You have a good lunch? Well, thanks for joining me this afternoon. My name is Luke Francl, and I work at GitHub, and I'm going to talk about some lessons that we learned from building the new GitHub Code Search. So if you've used GitHub Code Search in the last decade or so, you might have noticed it had a lot of limitations. It was really slow. It was limited in what you could search for. You couldn't even search forks. Well, my team is the team that was responsible for trying to fix that. And we did it by building a new search engine built from the ground up, designed specifically for searching source code at large scale. We call it Blackbird. And it supports exact substring match, regular expressions, code navigation like jump to definition, and it's fast. We can search across billions of files on GitHub and millions of repositories in only a few hundred milliseconds. But I think it's worth asking, why did it take so long to fix this problem? Well, I worked on the old system too. In fact, I was part of no less than 3 attempts to improve the old code search that all basically went nowhere. So why did it take so long? To answer that question, I think we need to back up a step and ask, what is the purpose of code search? Well, programmers have a lot of questions. Stuff like, where's the get user method defined? What does this error message mean? And why does this repository have so many YAML files? The purpose of code search is to answer questions like these so that we can help programmers understand code. And to answer questions like these quickly, we need to build an index. It just is not possible to scan across all the code without an index and answer them fast enough. So for a search engine, the process of building an index is called indexing. And it works sort of like this. First, we have to collect all our content, and we give each document a number. And documents contain terms that we want to search for, which I've represented here by colored boxes. This is called the forward index. We then use the forward index to build an inverted index, where we take every term and associate it with a list of IDs containing that term. That's called a posting list. Now, this is a really cool data structure because it supports fast querying. You can do Boolean operations by intersecting and unioning these posting lists. And there's been a lot of research to make this very fast. And that works great for a traditional document-oriented search engine. But indexing code is a little bit different. Because when we index code, what's changing is a repository. It's not like an article on a news site changed. The repository changed, and we have to go and figure out what is different from what was there before, or simply just enumerate all the files in the repository and also get their content. We also know that repositories are constantly changing. You're pushing code to GitHub or wherever you use, and you're modifying files. In Git, that's basically replacing that file with a new file. So when the search engine processes that, we need to figure out what files were modified, delete the old version, and add the new version. We call that a tree diff. And finally, for GitHub specifically, there's another wrinkle, which is forks. GitHub has a lot of forks, and forks are very cheap in our Git infrastructure. So it's essentially the same thing as a branch. When you fork a repository, that's super cheap. But for the code search system, that can be very expensive. Because, again, we have to enumerate the tree for that fork and index all the files, even if there's almost no changes. And this right here is basically why the old GitHub code search never supported forks. It's because if you forked a big repository like Kubernetes, that would force the code search engine to go and do a ton of work for something that's trivial for you. And we couldn't afford to do that, so we disabled it. Another aspect we should talk about for code search is tokenization. Tokenization is the process of taking input text and breaking it into tokens that the search engine can search for. So if we use like a English example, like the cats wore hats, we can break that into tokens by first splitting on white space and punctuation. Then maybe we take it to lowercase so that case matches don't matter. And then we can do stemming, which means removing endings from terms so that they match more concepts as opposed to specific things. And we can also remove stop words like the. For a traditional natural language search engine, there's not a lot of value in a posting list that simply contains every single document. That's going to match everything, and it's going to be slow. But as you can imagine, in code, little differences like this really matter. And that was the problem with GitHub's Code Search's original tokenization, which is represented by this regular expression here. So any character in this character class would cause a split. And that's not just spaces. There's also important programming characters like curly braces, parentheses, the equal sign, stuff that you might want to search for. Well, too bad, you can't. Let's see how this worked on some typical Java code. So we've got our Java code. First thing we're going to do is split on spaces and those special characters like angle brackets. Then let's take it to, oh yeah, the other thing that our code search did was split on case changes. So this was the only way we supported substring matches, was if there was a case change in the term. So we do that, then we take it to lowercase, and then as a final step, we would remove any character or any token that was less than 3 characters. And so you can see a lot of information got lost in this process, and you won't be able to search for those things. So why did we do it this way? Like, do we know better? Well, yeah, we knew better. Back in 2012, Russ Cox published an article called Regular Expression Matching with a Trigram Index, or How Google Code Search Worked. And in it, he explained how Google Code Search worked by splitting text into trigrams and then matching on those. And if you go back in the GitHub archives, back in 2012 when this was published, somebody wrote an issue and said, we should try this. But we were never able to try it. And the reason is simple. Trigram tokenization produces a lot more tokens. Every character is preserved. And we can do substring matches, which is awesome. But more tokens makes more storage space and longer indexing time. And we just simply couldn't afford to do it. Our system was trapped in a negatively reinforcing feedback cycle where it was expensive and it was hard to change. And those things work together to make rolling out any kind of changes really hard. What do I mean when I say it's expensive? Well, when we shut down the last remnants of the old code search system a couple of months ago, it was running on 312 physical servers with over 24,000 cores. Now, this isn't a lot for like a big cloud system these days, but for something that's not the bread and butter of your company, it's expensive. Also, it took months to reindex. So that means that in order to reindex, we'd have to spin up another one of these hugely expensive clusters, run it for months, and then shut down the old one. So that just made it really hard to experiment. And in fact, in the time that I worked on the old GitHub code search, the only times we ever reindexed were to evacuate data centers. That wasn't supposed to be a laugh line, but that's true. So when we were designing the new GitHub code search, we had a lot of end user goals, things that we wanted to be able to achieve, stuff like regular expression search. But we had one core goal that we've tried to hold to throughout the whole project for ourselves that's not user visible, and that's to make indexing fast. Our goal has been to keep the time it takes to build a new index from scratch down to 24 hours or less. How did we do it? Well, we rewrote it in Rust. Well, just kidding. I mean, sort of. We did rewrite it in Rust, and our Rust indexer can process more than 200,000 documents a second. But the real way we made it faster is to take advantage of the structure of our data. However, those architectural improvements matter, so let's take a moment to look at them. So the original GitHub code search indexing worked a little bit like this. We have on the edge github.com, which is the site you know and love. When you push code to it, it would send a message to a background job queue that would be processed by a background worker. Those background workers are also written in Ruby. They run the same code base, so they're having to boot up this huge monolith in order to do this. In order to get the file contents, they would have to make a get-RPC call, which is a homebrew RPC framework thing that we made for executing Git commands, to yet another copy of that big monolithic Ruby code base to get the contents. And then they would send it to Elasticsearch. So one of the big problems with this is that we were actually competing for resources with the other background jobs at GitHub. So things, if we indexed as fast as we could, we would actually cause problems for user visible features on GitHub. Like, you wouldn't get your notifications because we were rebuilding the code search index. Like, that's not okay. So for the new system, we designed it with a different paradigm. We still have github.com as the source of when repositories change. But now it publishes an event. And that event is consumed by our Blackbird crawler, which now talks to a high-performance Git API that's also written in Go to figure out what changed and to fetch the content. Then it sends it to another Go service, which does language analysis. This is a wrapping tree sitter and parses the files that we are indexing for you to extract stuff like class names, method names, function names, constants, to add them to the document. It then adds everything to the document and sends it to our Blackbird indexer. One of the key differences in this design is that the Blackbird crawler is not waiting for the indexer to commit the files to the index. It publishes them to a message queue. We use Kafka. And we have enough buffer space in there that it can just go as fast as it possibly can and not have to wait for the indexer. The indexer then also reads from the Kafka queue as fast as it can and indexes. So what about those improvements to indexing based on our data? Well, the first one we made was simply to index less data. And one of the ways we did that was to index fewer repositories. So a couple of years ago, we launched a technical preview of GitHub Code Search. Did anybody use that? OK, cool. So you know how in order to use that, you had to sign up for a waiting list, and then we would onboard you? Well, the reason for that is because we didn't have your code indexed. When we would onboard you, we would go figure out what repositories you had access to, and we would add them to the search engine right then and there. That's how it worked, because that is as far as we could scale the system at the time. So we launched with about 5 million repositories indexed, and then we grew the system over time. And at each order of magnitude, roughly, we've had to solve new scaling challenges. For our technical preview, we introduced document deduplication as one of the core features of the system. As we moved to a public beta, we had to introduce delta compression to reduce the amount of content that we indexed. And then as we approached our GA, we needed to eliminate unnecessary work. So let's go through each of these. First of all, deduplication. As I mentioned before, when we index code, we need to enumerate the files that make up that repository and add them to the index. And as I said before, this is why we didn't index forks, because you would have to duplicate all of the files. Well, the thing about Git is that every blob in a Git repository has a unique ID based solely on the contents of that blob, the Git blob OID. Instead, we could shard by the Git blob OID to automatically route every blob with the same content to the same shard. So any blob shared among multiple repositories will get indexed in the same place. And this reduced the amount of content we needed to index by quite a bit. And I think what's kind of cool about this slide is even though these are kind of stupid diagrams with just little colored boxes, you can see that there's less there's less content in the second slide because we deduplicated it. So that was awesome, and that was how we launched our technical preview. Because I think the other thing worth pointing out here is we needed to index more about each file than we had before, because we needed those trigrams, we needed the symbols. But as we grew the technical preview, we started running into some problems. And that is that when you deduplicate all the content, you need to keep track of where that content came from. And we call that the location metadata. And it sits next to the content, and it's got the path associated with that content. So if you do a search and you hit one of these pieces of content that was deduplicated and exists on a lot of repositories, we would have to scan through this table and figure out which one was relevant to your search. And that made the search really slow. So we needed a better way to solve this in order to make the index bigger. What we came up with, we call delta compression. Here's how it works. Imagine you had a network of repositories, and you could measure how far apart they are based on how much difference they have between them. So in this example, we have, let's say we have Torvalds Linux repository, and then GitHub has a fork of that, and there's a couple hundred paths that are different there. And then let's say that I have a fork of the GitHub fork, and I just changed a couple lines. My copy is much more similar to the GitHub copy than the Torvalds copy. So what if we could reuse all the work we've already done in indexing the Torvalds Linux repository for these child repositories? Well, essentially, that's exactly what we did. Here's how it works. So imagine you have a connected graph of repositories where the edges are weighted by how similar they are in terms of the number of changes. So if there's any graph theory experts in the audience, you may have noticed that this graph is not connected. But that's no problem. We'll just add a new node, a virtual node, that's connected to every other node with an extremely large weight. We don't want these edges to be used unless there's no other option. So once you have a connected graph, a connected weighted graph, you can run some pretty cool algorithms on it. And one of them is to compute the minimum spanning tree. Now, minimum spanning trees have been invented a couple times, but the first time they were invented, it was to optimize an electricity network where you wanted to connect every node with the lowest cost possible. And in fact, that's exactly what we want to do here. For us, the minimum spanning tree represents the most efficient way to reuse paths between repositories. If I rearrange the minimum spanning tree to a more familiar tree shape, I think that becomes a little bit more obvious. What we need to do is crawl these repositories in order such that the repositories closer to the root are crawled before their children. That's a level order tree traversal. We divide the graph into levels, or sorry, the tree into levels, and then we crawl the first level, then the second level, and then the third level. If this problem seems familiar, yeah, it's a leak code problem. And people say leak code isn't useful for your job. But how do we figure out how different repositories are from each other? Well, for that, we're going to use the symmetric difference of their trees. If we imagine repositories as sets with blob path tuples as their elements, the symmetric difference of two repositories, well, the size of the symmetric difference represents how similar or different they are. How do you figure this out? Well, Rust has a nice standard library that has a method that'll do this for you. You just create two hash sets with the SHA and the path buff as the elements in the hash set. And then you insert them all for each repository. And then you can call symmetric difference and get the count. But how much memory would this take? Let's do some napkin math. Let's say we have 100 million repositories, and they each have 1,000 files. Each blob OID takes 20 bytes, and then let's hash the path so that it's a consistent size. That's another 20 bytes. That would be 4 terabytes of memory in order to figure out this symmetric difference calculation. That's not going to work. This sounds like a job for cardinality estimation, like with hyperloglog. Hyperloglog is a probabilistic data structure that provides an estimate of set size while only using a small amount of memory. But can you compute the symmetric difference of 2 sets with hyperloglog? It turns out you can, using the inclusion-exclusion principle. So we count the size of the union of the 2 sets, multiply it by 2, and then subtract the size of the first set and the size of the second set, and that will give you your estimate. However, there is a problem with this. The problem is that hyperloglog accuracy is proportional to set size, not the size of the difference. So if you have 2 very large sets that are very similar to each other, you will get a pretty bad estimate in this case. And that wouldn't be good enough to work for us. So we needed to come up with a different solution. Fortunately, my teammate Alexander Neubeck invented a novel probabilistic data structure to solve this problem, the geometric XOR filter. Like hyperloglog, it supports set size estimation. However, it also supports addition and deletion of elements via toggling. This has a really big trade-off. You can't add an element back to a set. That's how sets usually work, right? Like you add an element, you can add it as many times as you want. Not with a geometric filter. If you add it again, that will mark it as deleted. But we use this property in order to model the changes between repositories and their parents. Because a child repository might delete a file, but then one of its children might add it back. And so we can model that with this. And crucially, the geometric XOR filter supports estimating the symmetric difference of 2 sets, and the estimate accuracy is relative to the size of the difference, not the size of the original sets. Using this new data structure, we were able to implement delta compression and reduce the amount of content that we have to index by a factor of more than 2. However, as we kept scaling up repositories in the system, trying to get to our general availability launch, reindexing was starting to take longer and longer. And we knew we needed to do something to solve that. That led us to try to eliminate unnecessary work. So first, let's talk about managing cluster resources. So when we started this project, we had 1 index shard that was managed by 1 server. So I guess it's not really a shard in that case, it's just the index. And we worked really hard to make this code efficient so we could index as much content as possible in it. But the problem is scaling is hard. We just got to a point where we couldn't fit any more repositories into our index. We needed to shard the index. So for our technical preview, when we launched, we had 8 shards on 8 servers. But pretty soon that wasn't enough either. We're going to need more shards. So we went to 32 shards in our cluster. But at this point, we were still 1-to-1 with each shard belonging to a single server. There was no redundancy. So we've got 32 points of failure here. If any of these went down, our cluster would stop working. And there was another problem that we needed to solve with this design, which is that, like a lot of search engines, Blackbird writes out immutable index files. They're append only. And so every 5 minutes, we write an index file to disk containing the contents that have been pushed in that last 5 minutes. These build up over time. And once there's enough of them, searches start to get slow because we scan through each of them sequentially. And if this runs long enough, we will literally run out of file descriptors and the indexer will crash. So our only solution was to rebuild the index from scratch and get rid of all these little sub-indexes. You know that line about how if you ship a project and you aren't embarrassed by it, you waited too long? Well, this was embarrassing, and there was no way that we could GA like this. What we needed to do is perform compaction to collapse up these indexes. Compaction is the process of merging these smaller indexes into bigger ones and get us down to one or two sub-indexes. The problem with compaction is that it's very computationally expensive, and it uses a lot of I/O resources. So when this is running, we wouldn't be able to index content incrementally, leading to index staleness, because this process will take an hour or two to merge them all together. Additionally, searches are still possible while doing this, but they'd be severely degraded because all the processing power on the server was being funneled into compaction. So to solve this, we designed a new system that we call dynamic shard assignment. Here's a diagram showing how it works. This is a screenshot from our admin tool. The numbers across the top are the IDs of the shard, going from 0 to 31. And each colored square represents a server. So you can see that there's the green boxes. Those represent servers that are doing incremental indexing and serving user queries. And then we expanded the size of the cluster by 6 hosts to 38 servers. And these extra hosts now run compaction constantly. And the incremental hosts don't worry about it. So this allows us to separate compaction off onto servers that are not in the query path and are not affecting user queries. But we're able to use the full resources of the server in order to do it as fast as possible. The other thing about this diagram that's worth pointing out is now we have redundancy. Each shard now lives on 2 hosts. So if a single host goes down, we no longer have to worry about the system going down. We can and have lost multiple hosts in our cluster, and everything still keeps working. So this is a system that we could be confident in going GA with and for being on call. But there was still problems because indexing was still taking longer and longer. We needed a way to reduce the amount of indexing work we were doing. To do that, we introduced a cache server. If you recall this diagram that I showed earlier about how our indexing worked, we have our Blackbird crawler that connects to the Get API to fetch content, and then it sends that content to the Blackbird analysis service for semantic analysis. Then it combines that stuff together and produces documents to be sent to the Blackbird indexer. So this is all well and good, but the problem with it is that when we would rebuild the index, we'd have to do all that work over again from scratch. So we thought, why not reuse what we already have? We introduced our cache server, which is written in Rust, and is actually a specialized version of our indexer. It's able to read the prior version of the index off of Blob Store and use it for document construction. So now the way it works, the Blackbird crawler still connects to the Get API to figure out what changed, but instead of constructing documents, it sends references to the Blackbird cache. If the cache has the document in the index already, it just goes ahead and publishes it, and then the indexer indexes. However, if it doesn't have it in the cache, what it does is sends a message back to the Blackbird crawler, which will then fetch the content from Git and send it back to the cache server for publishing. But crucially, we've also incorporated the symbolic analysis of programming languages into the cache server. We rewrote the tree setter bindings into Rust, and they're now running on a more powerful server. So it runs a lot faster. And with those two things put together, we were able to speed up our indexing time quite a bit. And the cache server is very effective. When we're rebuilding an index from scratch, we achieve a 99.9% cache hit rate for reindexing. And if you think about it, that makes sense, because most Git repositories, they don't turn over like every day. You're adding a file here or there, and those we have to go fetch. But most of the content in a repository stays the same from day to day. But I think what was somewhat surprising to me as I was working on this talk is that our incremental cache hit rate is actually over 50% on average. And I think that speaks to the amount of duplicate content that exists on GitHub and how many forks there are. So to conclude, what my team was able to accomplish that let us ship was to make our system more efficient and then use that efficiency to fix our iteration speed problems. If you remember this chart from about the old code search, we had 312 servers with over 24,000 cores running one search cluster. Our new system is much more efficient. We have 130 servers with about 8,000 cores. But this isn't a single cluster. This is 3 redundant clusters and 2 cache servers. Having that redundancy lets us not only have a backup for our index, but we have a cluster that's dedicated entirely to experimentation. So we are able to run experiments and change our index format all the time. Now, granted, these are not these are very powerful servers. They have tons of RAM and they have very fast NVMe drives. Thanks, Azure. And they are not cheap. But the point is, we can afford better machines because we've made the system so much more efficient. We've created a mutually reinforcing positive feedback cycle that's allowed us to quickly evolve the system to add new functionality. We keep track of index-breaking changes with a version number. And in the past 3 years, we have incremented that 50 times. That means we have broken our index format 50 times in the last 3 years. And that's not a bad thing, because we're not afraid to break our index version, because we know we can rebuild the index from scratch in just a couple of days. This means that we don't have to worry about tedious index migrations from one format to the other. We just start over. So each stage in the project, we've had to solve new scaling challenges as we grew from 1 million to 10 million to 100 and aim for 100 million repositories. What about the next order of magnitude? Well, fortunately, GitHub doesn't have this many repositories yet, but we may need to handle more data for other reasons, like branch indexing, which is one of our top requested features. Somebody was just bugging me about it at lunch. Or the fancy new vector similarity search that's all the rage due to AI. And you know what? The truth is, we don't know how we're going to solve this next scaling challenge. We don't know how we're going to handle this jump. But I have no doubt that when the time comes, we'll be able to figure out a way to achieve it. So what are the lessons from GitHub Code Search? Well, I realize you probably aren't going to build the world's largest code search index. But there are some lessons that I think you can take away from our experience. First of all, it can seem unwise to build software from scratch. When this project started, and remember, I worked on the old system, so when this project started, I was initially really skeptical. I thought it was going to take 2 years to build a search engine from scratch. Well, it did take 2 years to build a search engine from scratch. But building from scratch can make sense if you're able to use the structure of your data to beat the performance of off-the-shelf tools. There's no way we would have been able to build the user experience that we did for GitHub Code Search at a reasonable price with standard off-the-shelf search tools. Secondly, I think that at every level of scaling, your software will have new challenges. And you've got to be ready to deal with that as long as your software is alive. When you finally shut it down, like I had the privilege of shutting down the old code search, then you can stop worrying about it. But while it's alive, software needs to be able to adapt and grow. Finally, and maybe most importantly, I think it takes a lot of effort to make your system easy to change. And a lot of times that doesn't show up in user visible features. Our users don't care how long it takes us to build or rebuild our code search index. But it pays off for us because we're able to deliver features for them faster. So if you can, design your system to be able to be malleable and changeable as you handle the change that is the fate of all software. Well, thank you so much for coming to my talk today. I'd also like to thank all my teammates at GitHub. My teammate Manish is up here in front if you want to talk to him too. These folks all work with me to make GitHub Code Search great. And if you're interested, I have set up a little repo with some info about this talk. So thanks so much for coming to my talk. It's been a huge honor to be here to speak at the last Strange Loop. Thanks.